Q&A. And of course, if that's also for people online, you can ask a question either at the end or you can write them in the chat. We will read them at the end. And with that, I think I can give the floor to Jenna.
Thank you so much. Thanks everybody, and thanks to the organizers for asking me to give a talk. I'm excited to tell you about our high altitude instrumentation program. Hopefully this works. Okay, so I'm gonna give you some quick background on why we're doing this and what we're interested in looking at in the solar corona, and then I'm going to spend a lot of time in today's talk on our magnetometry pathfinder, which flew 2 Eclipse missions, and this instrument is called REDSoX. This was my PhD thesis mission, and then I'm going to talk a bit about what's next, both for future eclipses and moving beyond eclipses. So the solar corona is the outer atmosphere of the sun. It's visible during a total solar eclipse to the naked eye. And you can see a picture here on the left. And there's a bunch of notable features in this picture that are kind of immediately obvious. First, you see that the corona is very extended, especially compared to the much smaller solar disk. You see these features, these extended features called streamers, and these loop-like features. And in fact, the fact that you can view the corona at all in white light gives you another piece of information about it. And the reason you can do that is because it's filled with free electrons that are scattering light from the underlying photosphere. And the reason that these electrons are free is because the corona is really, really hot. So that's one kind of key piece of information about the corona, and that's also, from this image you see that it's not in equilibrium. It's so extended in contrast to the photosphere. Now, if you might get the idea that it's also very dynamic, not being in equilibrium. And in fact, if you play a video, you do see the kind of dynamic nature of the coronal plasma as the sun rotates here. And this video is it's not scattered white light emission. This is extreme ultraviolet emission, which again is happening because the corona is so hot. It emits very readily in the extreme ultraviolet. Now, you can see pretty clearly from these 2 images that what's underlying all of these physical phenomena is actually the corona's magnetic field. So you can see the plasma tracing out magnetic field lines here. You can see the magnetic field, kind of moving around. It's very dynamic and very much not a dipole field here. In fact, the magnetic field also stores the energy that is released in solar flares and coronal mass ejections. And so these phenomena happen when the magnetic field sort of gets twisted into a configuration that's unsustainable and then reconnects. So magnetic reconnection happens and it reconfigures into a lower energy configuration, releasing the magnetic energy as either light in a flare and or propelling plasma and magnetic field from the sun in a coronal mass ejection. So the left here just summarizes what I already said. Coronal magnetic fields are really important for understanding everything that happens in the corona. Unfortunately, they're really hard to measure. One promising way of measuring them is to measure emission lines in the infrared and visible. And this can provide, in theory, line of sight magnetic field strength and the plane of sky field direction. But the measurements are really, really challenging because the signal is very weak. And so where we come in, they are going to be made by DKIS, the Daniel K. Inouye Solar Telescope, in the next few years. This is just coming online on Haleakala on Maui. But DKIS field of view is relatively small. It has very high resolution. And so at the CFA, we're developing a complementary instrumentation program that's going to focus on high altitude versus ground-based observations. It's going to have a large field of view and significantly lower spatial resolution. And it's going to have, it's going to be able to make continuous and long duration measurements. So no day-night cycles, right? You can follow the sun across a rotation. And the emission lines that we're using to do this are magnetic dipole transitions. They're all forbidden lines. The corona doesn't, because it's so hot, it doesn't emit permitted lines in the IR or the visible. The the line intensity, so we measure these lines, and this is a remote sensing measurement of plasma properties, and it allows us to make a remote sensing measurement of plasma properties and magnetic fields. The intensity provides plasma temperature, density, and velocity, and the polarization provides the magnetic field. And the important thing that's driving us to longer wavelengths is the fact that the Zeeman splitting, the Zeeman sensitivity, which is the Zeeman effect, is how we would measure the magnetic field strength from the emission lines. This is more sensitive to magnetic fields the longer wavelength you go. And so that's pushing us to explore further into the infrared. And so I have highlighted here 8 infrared lines that are of interest and that have been measured by, or will be measured by, instrumentation built at the CFA. And so you can see that we measured a number of these lines with our Eclipse spectrometer that I'm going to talk about, a couple of them for the first time. And we're going to measure 5 lines with our balloon instrument, which I'll talk about next. And then we're going to measure all of these lines and many more with a Fourier transform spectrometer that we're going to fly in the 2024 Eclipse. And this is just an example of what you can get. This is from a group out in Hawaii who observes eclipses. You can see that the 2 different lines formed at different temperatures highlight different structures in the corona here. So this is a timeline of our instrumentation program. It all began with AirSpec, the instrument that we developed here in the SSXG group I think starting in 2015, and it flew in the 2017 Eclipse flight, the 2017 Eclipse over the US. We reflew it, we improved it and reflew it in 2019. And then we developed, we basically improved and separated out the image stabilization system so that it could be used with any focal plane instrument. And we tested that out. We hoped to test it during an eclipse, but the pandemic got in our way, and we tested it out with some observations of the photosphere in 2021. Now that image stabilization system is going to feed our Fourier transform spectrometer, which is going to measure all those lines that I mentioned in the 2024 Eclipse, which also crosses the US, so try to go see it if you can. Finally, in parallel, we're developing a balloon instrument, which is going to be a coronagraph. It's not going to rely on Eclipse, and it's going to have its demonstration flight in 2024 and its science flight in hopefully 2026 or 27. I'm going to just talk quickly about our our Airborne platform and our image stabilization system. This is a bit out of chronological order because we just finished this version of it just less than a year ago. But it sort of enables everything else we do on the airplane. And its predecessor enabled the previous Eclipse flights. So we fly on the Gulfstream 5 jet. This is owned by the National Science Foundation. It's housed out in Boulder or Broomfield, Colorado, right outside of Boulder, and it's operated by the National Center for Atmospheric Research. And this airplane is often used for in situ atmospheric measurements. So they sample the air and analyze the constituents. It didn't have a way to point to the sun. And so this is what we added using this gimbaled mirror to control azimuth and elevation. And here's why we need this. So the airplane flies very stably, but if you don't stabilize the beam, you can't actually point to one location on the sun. And we improved the image stabilization performance by adding closed loop control in 2019. And that allows us to actually point very precisely to a given location. And so this is proved out now, and we're going to use this for all future flights on the Gulfstream. Now, our first focal plane instrument for that image stabilization system was AirSpec. The goal of AirSpec was to characterize these IR lines to inform the development of future magnetometers. So AirSpec can't measure magnetic field, but we needed to just see what was out there before we could actually make magnetic field measurements. And so it includes a number of different components. It's a cryogenic spectrometer, so there's liquid nitrogen that needs to be poured into the spectrometer. That also means that the spectrometer is housed in a vacuum chamber. And the way it operates is it's a slit grating spectrometer, so it disperses the light using a diffraction grating. And we've cut the light up in a clever way. This was Leon's idea, but to actually get a fair number, 6 different emission lines on a very small detector at relatively high resolution. So even though we have a limited number of pixels. We flew 2 eclipses with AirSpec. The 2017 eclipse took place over the US, and the 2019 eclipse we observed over the middle of the Pacific. It was about a 5-hour transit to get there. And we then got to land and spend a day in Easter Island afterwards in order to refuel, and then we headed back to the mainland. Our base was in Peru. And so this is a video I think I've showed before at a CFA talk. So I'm sorry if some people have seen this, but this is what it was. This is what it's like on the airplane. So this was the 2019 flight. We had the sun had just completely eclipsed, so the total eclipse had just begun, and so we were very excited because we didn't. So everybody's excited because we didn't know how our closed loop imaging stabilization would do, because we had always tested it on the photosphere, and it's much harder to fit a circle to the limb of the moon. But it worked, and we pointed at a bunch of different locations in the corona. This actually shows where we pointed for both eclipses. We had coordinated observations in the extreme ultraviolet with ice, which flies on Hinode. And we got a very long eclipse in 2019, 7 minutes of data. We briefly lost the pointing in the middle because our image stabilization system was not perfect, but we got lots of great data. So what have we gotten out of that data? So we've made temperature. We're able to estimate the temperature using the infrared lines, and this is AIA data and shows that from SDO. And it shows that, clearly there were some temperature differences. There's the green line is cool and the red AIA data is hot. And we actually see this temperature difference in the intensities of the lines that we measure. So this cooler line, this iron 9 line, which is actually the same ion as AIA, the green, it's much stronger on the west limb, which is what you would expect, because that's where you see a lot of green cool material. And conversely, this sulfur 11 line, these were both measured for the first time by AirSpec. This sulfur 11 line was much stronger on the east limb, where there was hotter material. This one forms at a much higher temperature. And we're working on a paper with Giulio Zazana, which actually is going to publish quantitative temperature estimates from the AirSpec data, as well as ICE and AIA data. We also got some density measurements. We had a density sensitive line pair. And so for the first time, we got density measurements using the sulfur 11 IR line pair. It's a little bit tricky to do this in the infrared, because you have emission out, a lot more emission outside the plane of the sky than you do in the extreme ultraviolet, because the lines are partly photoexcited, and there's a lot of photospheric light in the IR to excite them. So it was nice to do a proof of concept that we could actually measure density here. We potentially found 3 new lines that were right at the AirSpec detection limit, and so we see them strongest when we're looking very close to the limb, almost at the very end of the eclipse. And that's why you can see a bunch of hydrogen here, because we're not just looking at the corona, we're partially looking at the chromosphere as well. But the lines highlighted in orange are new. We think we know what they are, and we can get a decent measurement of their wavelengths, but the wavelength is pretty different from the theoretical values. And so one goal for the next couple of years is to measure them using Amy's EBIT, which is in the labs at CDP. We tried to do this measurement over the summer, and our detector just wasn't sensitive enough. So moving forward, we're hoping to get a more sensitive IR detector to measure EBIT plasma and confirm the wavelengths of these lines. So this is what AirSpec is doing right now. It's not going to fly any more eclipses, but we are going to fly another eclipse, and we're going to fly this eclipse in 2024 with a new instrument called the Airborne Coronal Emission Surveyor, or ACES. And this is the Fourier transform spectrometer that is going to allow us to get all of those lines that I mentioned. And in fact, there's many, many lines in the 1 to 4 micron passband that we might see depending on how bright they are. We've predicted that we have a reasonable shot at seeing all of these lines, that they all should be bright enough. But you can see that a lot of them, the ones in bold, have actually never been seen before. And so we're not really sure what their intensities will be. And that's one of the reasons we're doing this. We're trying to, ACES is going to kind of open the 1 to 4 micron corona from above the atmosphere to actually allow us to characterize that wavelength region, because pretty limited measurements exist right there, right now. And so we're collaborating with NCAR and National Solar Observatory on this, and we are taking a solar feed from our image stabilization platform. We're going to observe probably over either Texas or Mexico, where the eclipse is the longest and where we have a good angle to the sun. That's always important because otherwise you might have to place your instrument in the middle of the aisle or somewhere to catch the solar beam, somewhere where the pilots don't like you to be. And with ACES, we're not, again, measuring magnetic field, but we are measuring temperature and density. We're measuring collisional versus radiative excitation in the IR lines. And radiative excitation, as I mentioned before, is what allows them to stay bright so far out from the solar disk. And we're going to measure elemental abundances. So ACES has the ability to observe over a really wide passband at high spectral resolution, which makes it very different from AirSpec. AirSpec, even though we did some clever things with the chopping up the passband to make it fit on the detector, we were limited by the number of pixels. So there was a resolution spectral range trade-off. That doesn't exist in ACES. ACES is a Fourier transform spectrometer, which means it has a moving mirror, which changes the path length between the two paths of light in the instrument. And when the paths recombine and interfere, you actually you measure what's called an interferogram, which is the Fourier transform of the spectrum that you want to measure. And so you have to move that mirror very steadily and at a nearly constant velocity. And then you can get a spectrum essentially, and we're gonna at every single point along this this slot field of view. Oops, I'm not gonna go to that. So that's ACES. We're going to get context images over this larger field of view, and we'll get spectra over 100 or so pixels here, going roughly radially outward from the sun or from the photosphere along a coronal streamer. And then we finally are going to measure magnetic field with our next instrument, and this is a non-eclipse instrument. So we're moving beyond eclipses, and we're moving away from just measuring plasma properties to measuring magnetic field with a coronagraph, a balloon-borne coronagraph. So CORSAIR is the name of this instrument. It's a coronagraph, a spectrometer, and a polarimeter all in one. The polarimeter is what allows you to measure magnetic field, and that's why the other instruments couldn't do that. This again is a collaboration with the High Altitude Observatory as well as the University of Hawaii. And we're, in this case, instead of surveying a large IR range to kind of just see what's in there as far as emission lines go, we've picked we've carefully chosen 5 infrared lines that can give us very specific information on density, temperature, line of sight velocity, and magnetic fields at different temperatures. So tracing out different temperature structures. And so you can see, you know, in what our hopes of the level 2 data will look like right now. So we have a fairly sensitive measurement of line of sight magnetic field over 1 hour, although it's really noisy. And then plane of sky field direction, which has been measured by other instruments, is much higher signal to noise ratio. And then we have velocity measurements as well. The way we do this is we have this multi-slit spectrometer, and in the eventual science flight, we'll have very, very narrow filters. These don't exist yet, and the development effort for them is proceeding in parallel with our first iteration of the instrument. And what that allows you to do is you can get kind of a 3D cube, so spatial by spatial by spectral, all at once, because you have 2 slits that are so close that they give you reasonable spatial coverage of the sun, but they don't actually, each one is dispersed, but the light doesn't actually overlap because you have these very narrow filters. And so CORSAIR is going to fly on a high altitude balloon. NASA Wallops is building the gondola for us. This is a model of the design so far. It's a really complicated instrument that doesn't translate immediately to space because there are a lot of mechanisms. So it's a refractive instrument, mechanisms refocus in each wavelength. We have a vacuum chamber up there Again, because we have a cryogenic spectrometer, it's measuring out to 4 microns. And then the gondola itself does the pointing for us, so that's nice. We don't have to worry about that. They can point to within an arcsecond of sun center, which is really impressive with this massive payload. But we are going to have to correct the roll of the image. They don't do that, the rotation around the line of sight. And so we're, the engineers at CDP are right now designing and going to be building this big roll stage that rolls this massive 1,500-pound telescope. And so I think that's all I have to say. There's a whole bunch of people involved in all these projects that I wanna give credit. But that's it.
Thank you so much. Do we have any questions from the audience in person?
Very interesting talk. I have a question about the heights that you go to measure the magnetic field. What is the largest height?
You mean above the limb?
Exactly.
Yeah, that's a good question. I think for if we go back to that picture, these are predictions based on an actual model done by Maxim Kramer out at University of Hawaii. And so you can kind of see in 10 minutes, we can get the plane of sky field direction all the way out to 1 solar radius from the limb. And our field of view, in fact, is 1 solar radius from the limb, so 2 plus or minus 2. But you can see that we're going to be limited by the sensitivity for the line of sight magnetic field. And in an hour, we're probably only going to get maybe 0.2 above the limb in an active region. We can potentially, if we just integrate longer and give up the time resolution, we can of course do better than that. It's just photon noise limited.
So what kind of hole do you cut in the fuselage of your Gulfstream 8?
Yeah, that's a good question. So they have a hole cut in it already. I don't know if I have a good picture of this. You can see, let's see, you can see here, there's a, mounted in the plastic Gulfstream window, there's a much smaller sapphire viewport. And so this is something that already existed. And it's composed of 2 panes of sapphire glass. They have to be, a certain thickness, of course, because it has to hold the pressure. And the sapphire was chosen for our particular application because of its passband. But so we take this small window and we mount it in one of the larger holes that already exists in the plane. And this plane has extra, it doesn't just have the side windows, it also has some overhead viewports that you can't really see anywhere because it's been modified for research. Oh, sorry. How do I do it?
So it should be. So John, can you try to ask your question? Let's see if we can hear you.
Yeah, can you hear me?
Yeah.
Perfect, thanks.
Okay. The Fourier transform spectrometer requires that the thing that you're looking at be constant while you're taking the scan. And you have a gradient in the coronal brightness. So do you have really tight limits on the pointing in order to keep the thing you're looking at constant?
Yeah, that's a good question. So we're trying to, essentially what we're doing is we're measuring the Fourier transform of every, I think, 20 by 20 arcsecond pixel. So there is going to be some averaging that takes place within there, and I guess we're not going to see kind of outside of that. And our pointing right now, so our pointing has to be much less than that, and our pointing right now is kind of six arcseconds. So I think it'll be okay, but you're right, it is a concern.
Okay, please.
Yeah, sorry, I might have missed it, and I apologize if I did, but what's the scan speed duration across your field of view?
For the Fourier transforms, so the
Yeah.
mirror scan, you mean?
Yeah, how, like you're doing this rapidly, or is it a very?
It's a pretty slow scan, just because it's limited by the readout rate of the detector. And in fact, that's why we have this very narrow, long field of view, because to get a full 2D field of view, it would have just taken much longer to read out, and we can't scan as fast as we need to. So we're doing around 30 scans in a 6-minute eclipse. Whatever that is, I think I might have the number, but so it's slow for an FTS certainly, but it's pretty fast. Something like I think an 80 microsecond exposure time for each position.
Question
Yeah,
from
please.
high altitude up here. Is there any hope of seeing these lines in an active region on the disk, or is the continuum just overshadow everything?
The continuum overshadows everything. And so we essentially need the disk to be blocked to get any hope of measuring these lines. And so either we rely on the eclipse to block it for us, or we'd have to build a
That's
coronagraph
what I
to
was
block
afraid
it.
of, yeah.
Yeah, it's too bad.
Thank you.
Otherwise, it would be great.
Any more questions from anywhere, including the Zoom? No, seems no. Okay, let's thank our speaker again. Okay, and let me gear up to introduce the second speaker, who's almost nearly local. She's from MIT, kindly came in person to visit us. So she's Sarah Trowbridge Heine, I hope I pronounced correctly. So she did an undergraduate in physics at MIT, finished in 2008, then PhD also at MIT in 2014, working on the Micro-X rocket payload. She works primarily on instrumentation, and she's member of the X-ray polarimetry lab working with Herman Marshall, who some of you probably know, to develop novel techniques using Bragg reflectors for soft X-ray polarimetry. She also works on a cryogenic neutrino scattering experiment called Ricochet, I think, with Joseph Formaggio. That's I pronounce it Italian way, sorry, probably not the American pronunciation, in the laboratory for nuclear science. Her main science interest is supernova and charge exchange. I'm happy to read that. But hers really lies in building hardware to do science, and that's the main topic of the talk of today. And with that, the floor is yours. Thanks.
Thank you. All right, thanks everyone for having me, for inviting me here, and thanks to the organizers for setting this up. So I'm Sarah Heine. I'm a research scientist over at MIT, and I'm kind of an instrumentation mercenary, kind of going wherever the interesting things to build are. So as many of you probably know, the IXPE, which is an X-ray polarimetry mission, just launched recently. This was their first light image of CORSAIR, which is a remote over remnant that's close to my heart for Micro-X. And their first paper came out, I guess, a few months ago, showing that they can see polarized X-rays from a magnetar, so that's working really well. So I will be the first to say that I'm not real focused on this science, but for those who are, basically you're interested in looking at polarization for anything that you want to understand the magnetic fields in. So IXPE is looking in the 2 to 8 keV region, and they're looking at all sorts of different winds, magnetic field configurations on high energy things. So what we would like to contribute with our instruments is to add to what they're doing with soft X-ray science. So you can see this is from neutron stars with magnetized atmospheres. This is the IXPE band up here. You can see in our band here, which is shown in red, that we're interested in, there are some interesting lines and that sort of thing. So we can contribute to understanding these things more fully by broadening the spectrum we're looking at. And the other thing that REDSoX, which I'll tell you more about later, is good at doing is doing spectropolarimetry. So we're not just going to get a single number for what's the polarization, we're going to get what's the polarization as a function of energy. So that should be really interesting for a lot of these sources. So similarly, this is looking at AGN. You can see if you're looking at IXP, you're going to get one of these spots. You can test these models a lot better if you have more than one number to compare it to. All right, so this is our main idea of what our polarimeter looks like. So you have light coming in from some astrophysical source, hits a focusing optic, then goes to a dispersive optic. In our case, we're using cat gratings, which some of you know and love, and I'll talk more about later. But these disperse the spectrum out to a Bragg reflector, and our Bragg reflectors have are designed so that the energy of the Bragg peak is different along, it changes along the length of the mirror so that it matches this the dispersion. And so the portion of the light that is polarized along the surface of this is going to get reflected and hit the detector. So here's just another schematic of what this will look like. So like it's focused in, we have an imaging detector as well. So it's going to miss the gratings and hit the imaging detector. And then you also have where the gratings are going to shoot it over to this polarizing mirror. It'll bounce off the mirror and hit a CCD. And we're going to put a few of these in different orientations so that we can measure different polarization directions. All right, so now that brings me to REDSoX, which was Herman's tortured acronym. He really wanted that. He got permission from Major League Baseball to use it. So it's the rocket experiment demonstration of a soft X-ray polarimeter. So it's a sounding rocket, which means that it's going to go up on a rocket. It's going to sit above the atmosphere for about 5 minutes to observe and then come back down, hopefully on a nice soft parachute ride and land back down so we can collect it again. We have about 5 years and $5 million to do this. So it's going to be a very small local effort, but should be a lot of fun. We're hoping to get a minimum detectable polarization of 17%. And at the moment, we're trying to decide between Mercurian 421 or HEREX 1 as a target. So one's a blazar and the other is a neutron star binary system. So our optics are these Walter 1 nickel shell optics. We're leveraging the fact that Micro-X had some of these mandrels made, but never used them. So we're just going to replicate shells off of those, which helps our costs. We'll get 15 to 25 arc second half power diameter. We'll use these cat gratings, which are made locally at MIT as our dispersive optics. We have some questions on the detector system at the moment. We're trying to decide between either using CCDs, which would be liquid nitrogen cooled, or possibly switching over to CMOS. And our mirrors that I talked about are laterally graded multi-layers, which would be made at Lawrence Berkeley. So here is sort of the photon's eye view of what will happen inside the rocket. So out here is the skin, and then these layers here are the optic shells. So it'll come in, hit off of this and start focusing. These gold things here are the gratings. So each mirror has, each one of these mirrors, which are the laterally graded multi-layers, has 2 banks of gratings that feed it. So like these 2 fit this guy over here that are sort of aligned with it. So you have 6 banks of gratings, 3 multi-layer mirrors, and each of these multi-layer mirrors has a little CCD associated with it down here. And there's also an imaging detector in the center. So we've stair-stepped these gratings so that they can meet the Bragg, they can all sort of come in and meet the Bragg condition in the right way at our mirrors. And as you can see again, so there are these pairs of gratings, they're kind of at different spots just to satisfy this. So we've got a ray trace here, which I don't expect you to be able to make any sense of, just to know that we have done it and it works. And here's a closer look at what the focal plane would look like. We've taken out one of the mirrors here and one of the detectors so that you can see what's going on. So this is the multi-layer mirror. There's one here and there's one missing. So the light comes in, bounces off of here and goes to a detector that will sit about here. And so you have them rotated at 120 degrees so that you can get each of the 3 polarization directions, as well as the imager in the center. And the plan is that the imager helps us to make sure our pointing is right, because our pointing is very important with this. So we will get our first image, and then the plan is to kind of joystick around a little bit to make sure we're really centered properly during the flight. All right, so more about our gratings. These are critical angle transmission gratings. These are the same guys that planned for Arcus, so some of you know them very well. They're manufactured at the MIT Space Nanotechnology Laboratory, which is just down the street here. And they're etched from silicon wafers. So they have these hexagonal support structures and lots of little grating bars. So each cell has this kind of larger silicon support structure and these smaller silicon support structures, and then a ton of little grading bars that they etch into it. Here's what one looks like by the eye, and we're a big fan of this picture in our lab because you can see that it's dispersing the light from the lamp behind it. So this right now is one of the is a big grating, bigger than we'll use in REDSoX, but it is mounted on a holder that we use in our beamline. And you can see, if you look closely, you can see these little support structures here. And this is sort of the efficiency measurement that we tend to make in our beamline. So we have a single energy of light and we send through, and we can move the gratings in and out of the beam to see what we're getting. We had about a month when my assignment was, can you break these things? Which was really fun. So one of the things that is going to happen in REDSoX is that the beam that's hitting the cat gratings is in the middle of focusing, so it's not coming in at the same angle. So we wanted to know if we could bend the gratings so that the light can be coming in, hitting it all at the same angle. So it's hard to see in this image, but this is actually a curved surface here. It's about a 1.7 meter radius of curvature. And it turns out you can curve it. The efficiencies don't change, and it doesn't break it. So that's good. We've also shaken the gratings and not with these, but we've also, with the mirrors, we've also cooled them down and done all sorts of tortured things to them to make sure that this stuff will work on a rocket. So for alignment for the grating assembly, we'll want to make sure these things are all very closely co-aligned. Our system that we built for doing this is a copycat of what they were using for Arcus. So we basically have a UV laser that goes and bounces off each of our gratings and comes back and tells us, are they aligned in the right way? So this is a picture of our very not professional looking system in the lab, but again, it works. All right, so moving on to the mirrors. These are laterally graded multi-layer mirrors. So this is showing along the surface of the mirror, you have all these Bragg peaks that are at different energies. So this is just mounted on a nice stable stage for use in our beamline. But here's another plan that we had at one point. I'm not sure if we'll use it on REDSoX, but so each combination of elements that you use to make these coatings gives you a different bandpass. So this is 3 different combinations of coatings. And one idea to extend our bandpass was to possibly kind of mosaic these things. So we played around in our Can We Break This month of can we cut them and have them still work? And it turns out we can. If we put the right coating on while we're cutting it and then take it off, it works well. All right, so then for detectors, we're still trying to decide between CCDs and SIDOR CMOSs. So we just found out that the program was approved. And this works out really well for our lab because we happen to also be working with SIDOR with a small business grant to help them develop off-the-shelf flight-ready CMOS detectors. So it works very well with us because if that works out, then we can just kind of plunk it onto the rocket, which would be perfect. So the CCDs obviously have more flight heritage in the X-ray. MIT has been flying CCDs since probably before I was born. The CMOS is a lot less expensive and has lower cooling and power requirements. It's just more risk because it hasn't really been tried in flight in the X-ray very much. But we were hoping to make it work because that would be mutually beneficial for us and the company. All right, so all the development is happening in the MIT Polarimetry Laboratory. This was originally the beamline that was used for testing the HETG gratings for Chandra. So everything's that you see is pretty much 30 years old, but it again works very well still. So we have a Manson source in the X-ray, a rotating flange here, and then we have a beamline that can either be 11 or 17 meters long, depending on what tubes you put in, with 2 big chambers at the end. So these are our 2 main setups that we use in the lab. So one is for grating testing. So we have our X-ray source bouncing off one of these polarizing mirrors. And what that allows us to do is not only send a polarized beam down the system, but also send a monochromatic beam, so that you put your spot on one spot on that polarizing mirror, which selects out whatever the Bragg peak energy is at that location, and gives you basically a monochromator that you can send down. So then we have the grating sitting in the grating chamber after a collimating slip, and the X-ray sitting in the detector chamber. This other configuration is what we call polarimetry mode. So this is where we're kind of trying to reproduce this polarimeter concept that we have. So you do the same thing with the source, you're sending down a polarized beam, but instead of putting your CCD here, you put another polarizing mirror bouncing to having your CCD vertical. So depending on how you rotate this flange, as you rotate the two mirrors against each other, you see the signal going up and down, and you kind of prove your concept that you're able to measure that polarization. So this is what it looks like inside the grating chamber. The light is coming from here. We have this aperture plate and slit plate that allow us to kind of just down sample this big beam of light that's coming in. This is the grating tower. So I showed that picture of the grating sitting on a little handle before. That just slides into some nice little spots here, and we're able to go up and down, rotate while the thing's under vacuum. Here's the detector chamber. This is a Princeton Instruments CCD that has an optical blocking filter on it, and a shutter that's coordinated with the camera so that we close it while we're reading out, and we get better efficiency measurements. Other things that we can play with that we have not yet put into our system, we have a focusing optic that the plan would be to put it in that grating chamber so that you can make a sort of kind of focused beam that's going into your gratings and your the rest of the system, so that you get more or less an end-to-end test of this whole system. We also have future plans once we fly REDSoX, and hopefully sooner than that, even we have another version of the polarimeter, which is GOSOX, the Globe Orbiting Spectrometer. This is designed for the Pioneer program, so it would be a small ride share opportunity that flies for about a year. We've baselined CMOS for this because it's just easier to keep that going in space. But the challenge in the Pioneer program is, since it has to be on that ride share, it has to be 1.2 meters or shorter, which is hard to do with X-rays because you've got that focusing off, that grazing incidence optic. So you can see that when we design the spacecraft, the end of our thing is right at the ride share ring, and it extends right to the edge of the envelope. So that's another project that hopefully will happen once we prove that we know how to do this. So our next steps is first to make all these design decisions I've been talking about. So what the multi-layer is going to be exactly, and whether or not we're going to mosaic it, what the detector will be, and which will depend on playing with these side-door CMOSs, and then kind of just put everything into the beamline and test it. And we're targeting flight in the third quarter of 2027, which will be from White Sands Missile Range. So stay tuned. Hopefully see it soon.
Do we have any questions?
For the CMOS that you're getting from the sidewalk, what are they claiming the performance looks like? Do you have any sort of summary on what they're going to be able to achieve in terms of threshold energy resolution?
We don't have a very good idea in our bandpass. So that's some of the project is it's sort of they're giving us the detector for free, and then we tell them.
Oh.
Yeah, we've seen some QE curves that look very good in our bandpass, but a lot of these commercial CMOS systems all use this G-pixel CMOS dye that comes from China, and that company is like, they're very opaque. So they're sort of like, here it is, take it or leave it. But yeah, so we'll see.
When you were describing the imager, you used the phrase joysticking. Was that just a phrase, or are you going to be actually controlling the the orientation in flight.
It will actually control the orientation in flight. So I don't think it'll be a real joystick. That would be cool, but my guess is that what it ends up being is you get the image back and you say, I want to move this much X, this much in X and this much in Y, and then they reorient. But it has to happen fast because we only have 5 minutes to look at it. So I think we get an image in 30 seconds and then move it and then.
Second question, for REDSoX, did you consider like a new star style extending boom in order to fit into a tighter component? or-
Yeah, we did. The problem with the booms is that they're anytime you put something moving in, it's another element of risk and another high element of cost. So it was sort of, do you put your energy and time and money into figuring out how to do it smaller, or do you do that into the boom? And we figured the smaller one was the lowest risk.
Any more questions? From person or online? No? Okay, I would say let's thank our speakers of the day. See you next week.